In this video I am going to discuss about a relations which is from chapter 1 class 12 maths, and this is the first video on relations. A relation is any set of ordered pairs. Here I have taken an example R, which is the set of ordered pairs. If any two elements written within first bracket, then it is called an ordered pair, and if two elements are written in second bracket, then it is a set. So we have to keep in mind this. So here we can see the set R, it is the set of ordered pairs. 2 3 is an ordered pair, 4 5 written in first bracket is an ordered pair, 6 7 is another ordered pair, and the collection of ordered pairs, that is the set of ordered pairs, is a relation. Now before we discuss in detail about relations, we will have a quick revision about this topic: sets, subsets, and number of subsets. Taken an example here, a set is a collection of well-defined and distinct objects. Taken an example, A is equal to a set formed by the elements A, B, C, and D. Now if we take all possible collection of elements from this set A, taking one at a time, taking elements 2 at a time, and taking elements 3 at a time, and so on. The first collection will take 5, that is the empty set, and the last collection I am taking the set itself, that is A, B, C, D. Then all these possible collections are called subsets of set A, and total number of subsets, it is given by 2 to the power n, where n is the number of elements in set A. In this case we have 4 elements, that is n is equal to 4. So total number of subsets we will have 2 to the power 4, that is 16. To study in detail about relations, I am taking two different examples. In one example I am taking two different sets, A and B, and another example I am taking only one set. Now let us see this case in which I have taken two different sets. The Cartesian product of sets are found like this. It is the set of all ordered pairs with 2 4 giving first pair, 2 5 giving second pair, 2 6 giving the next pair, and then with 3 4 3 5 and 3 6. These are the all ordered pairs in which the first element is coming from the first set, and in every ordered pair the second element is taken from the second set. Now this is the Cartesian products of A into B we got, and it is also a set of ordered pairs, and I am going to write all possible subsets of this set A into B. And all possible subsets, it is written like this: the collection of elements taking one at a time. So 2 4 is a subset. Then collection of elements taking 2 at a time. So if we take first pair and second pair, this is also a subset. And then we will take all possible collection of elements taking 3 at a time, then it is also a subset, and so on. Collection of elements taking 1 at a time, collection of elements taking 2 at a time, collection of elements taking 3 at a time, and then every time the first collection we take is empty set phi, and the last collection we take the set itself. Because every set is a subset of itself. So all these collections are the subsets of A to B, and total how many subsets, how many collections will be there is given by 2 to the power n formula. But here total n is the total number of elements in these sets. If a set A has m elements, set B has n elements, then in this product, Cartesian product A into B, we will have m into n elements, and hence total number of subsets will be 2 to the power m into n, because number of elements here in this case, in this Cartesian product, is not n, it is m into n. So total number of subsets will be 2 to the power m into n. Now we have written here R, that is relation, is any set of ordered pairs. And here we can observe every collection, that means every subset here is a set of ordered pairs, and hence every collection is a relation. This is a set of ordered pair, it is a relation. This is also a set of ordered pair, and it is a relation. And hence every collection, that is every subset, is a set of ordered pair, and hence is a relation. So these are the total number of relations will be given by the formula 2 to the power mn. This empty set phi is called empty relation, and this set A into B itself is called universal relation. It is the universal relation. Now, what we have understood from here is total number of relations from A to B. Total number of relations from A to B is given by the formula 2 to the power mn. And if we want to write total number of non-empty relations from A to B, that means we will reject this phi, except this phi remaining will be 2 to the power mn minus 1. So this is the formula to find total number of relations from set A to B, and this is the formula to find total number of non-empty relations from set A to B. That means we are rejecting phi. Now coming to this case, in which taken a single set and then I have found the Cartesian product of set A with A itself. If A has n elements, then A into A will have n square elements. And then if we write all possible collections, that is possible subsets, like here taking elements one at a time, from this collection taking elements one at a time, then all possible collections 2 at a time, 3 at a time, and so on. First is phi, last collection is the A into A itself. Then every collection is a relation in set A, because here only one set, and every collection is a relation in set A, and total number of relations will be in this case 2 to the power n square, because we have here elements n square. First set has n, and second set is also A itself, and it will also have n elements, so n into n. In this case we will have n square elements in A into A, and total number of subsets, that means total number of relations will be 2 to the power n square. And exactly same as we have seen in the case 2, this phi is called empty relation, and this set A into A is called universal relation. And first case we have seen total number of relations from set A to A itself is given by 2 to the power n square formula. And if we want to reject phi, then we will have total number of non-empty relations from A to A will be given by 2 to the power n square minus 1. We are rejecting 1, that means we are rejecting this empty set phi. So this is about relations from set A to A itself, and in this case relation from set A to B. And in class 12 maths, relation study will be mainly confined within set A to A itself. Now if we want to write a relation definition, we can write like this: a relation from A to B is given by the set of all the ordered pairs in which first element is in first set and second element is in second set. This is the definition of a relation from set A to B. And in this case, if we want to write the definition, from set A to A itself is given by all the ordered pairs in which A and B both are in the same set A itself. So this is about relations. There are different types of relations. One is reflexive, another symmetric, another is transitive. Taking an example, a set A with elements ABC. Now reflexive relation is like this: for all elements A belongs to set A, AA must be there in the relation. Taking an example, set A with 1, 2 and 3. Then a relation in which every pair of all the identical elements, that means for 1, 1 must be there, for 2, 2 must be there, for 3, the pair 3 3 must be there, and there may be more elements, may not be more. Then this relation is a reflexive relation. And this definition A belongs to R can also be written in this form, A related to A. So the reflexive relation is, for every element in set A, the ordered pair of identical elements must be there in the relation. For 1, 1, 1 must be there, for 2, 2, 2 must be there, for 3, 3 must be there, and then only the relation is reflexive. There may be more elements, may not be there. So this is about reflexive relation. Symmetric relation is not for every element in set A. It is, if a pair is in the relation, then its reverse pair must be there. Reverse pair means the pair reversing the order of elements. That means if AB is there in the relation, BA must be there in the relation. I'm taking an example, a relation in which 1, 2 is there, then there must be 2, 1. There may be more elements. So whenever a pair is there, its reverse pair must be there. That means reverse pair means the pair formed by reversing the order of elements. Then the relation is reflexive. Relation is symmetric. And this symmetric relation definition can be also written in this form. If A related to B, this implies B related to A. So this form of writing, this definition can also be written in this form. So symmetric relation is, if a pair is there, then the pair reversing the order of elements must be there in the set. Then the relation is symmetric. Now coming to transitive relation. If AB is in the relation, then BC is in the relation, then the pair formed by first and the last, that means AC, must be in the relation. And this transitive condition is applied only when this B is common. AB, BC, then AC must be there. Taking an example, if a relation having 1, 2, 2, 3, now in this case both the pairs 2 is common. It is 1 to 2, then it is starting from 2, 2 to 3. Then if middle one is common, then the pair made by the first and the last, that means 1, 3, must be in the relation. There may be more elements, may not be more, but whenever two pairs are found in which the middle element is common, then the pair made by the first and the last must be in the relation. Then the relation is transitive. Then transitive relation, one more definition is there. This is the first definition. Another definition is, which is very important, we often do mistake regarding these definitions. If a pair AB is in the relation and another pair BC is not in the relation, and the pair made by first and the last is also not in the relation, then also relation R is transitive. Example, if a relation AB we have in which 1, 2 is there and with 2 no other pair is there, then 3, 4 and with 4 no other pair is in the relation. I am ending it here. 1, 2 with 2 no pair is there, 3, 4 with 4 no pair is the relation, and hence this relation R is transitive by this second definition. I am taking one more example. This is one example for this set. Another example I am taking, if a relation in which only say 2, 3 pair order with made by 2, 3, then the relation is also transitive, because 1, 3 is there and with 3 no other pair is there, and hence by this definition this relation also is a transitive relation. So this is about transitive relation, symmetric relation and reflexive relation. Next, two definitions. One is equivalence relation. A relation which is reflexive. If a relation is reflexive, it is also satisfying the condition symmetric as well as transitive. If a relation is reflexive, symmetric as well as transitive, then it is called a equivalence relation. And then coming to equivalence class. And to understand equivalence class, I am explaining with an example. I have taken two different examples here. a relation made by the ordered pairs given here, and I want to write equivalence class of 1. Equivalence class of 1 is the set of all those elements which are related to 1. In this case, I can see 1 is related to 1, so I can write 1 because 1 is related to 1. 2 also is related to 1. 3 is not related to 1. 5 is related to 1. So equivalence class of 1 is the set of all those elements which are related to 1 under the relation. In this case, second case, if I want to write equivalence class of 1, it can be any elements. Equivalence class of 2, 3, 4, any elements. In this case, equivalence class of 1, okay, I'll write equivalence class of 2 in this case. Then what are the elements related to 2? In this case, the only elements 4 is related to 2, and that is the equivalence class of 2. If you want to write equivalence class of 1 in this case, then all those elements related to 1 here, 3 is related to 1 and 7 is related to 1. So this is the equivalence class of 1 because these are the elements which are related to 1 under the relation. So this is about equivalence relation and equivalence class. Just for clarification, taking an example in which I have taken a set A with elements 1, 2 and 3, and I want to write reflexive relation. Whenever you want to write reflexive relation, you must write all the ordered pairs of identical elements for every element in set A. For 1, 1, 1 must be written. For 2, 2, 2 must be written. For 3, 3, 3 must be written. This is a reflexive relation. I can write more relations reflexive, and whenever I want to write reflexive relations, I must first write all these ordered pairs of identical elements. I have to write 1, 1, 2, 2, 3, 3 must be written, and then I can write any more elements, say 1, 2. This is also a reflexive relation because for every element, pair of identical ordered pairs are there. We can write more reflexive relations, but in every reflexive relation, this must be there. For every element, pair of identical elements must be there. Symmetric relation, whenever we write a pair, say I'll write 1, 2. If I write 1, 2, then there must be 2, 1. This is a symmetric relation. For 1, 2, 2, 1 is there. For this 2, 1, 1, 2 is there. I can write more relations. Say another relation 1, 2, then there must be 2, 1. If I write any element, say 2, 3, then there must be 3, 2. Like this way we can write more reflexive relations. But transitive relations, I'll write one relation, say 1, 2. If 1, 2 is there, 2, 3 is there, then the middle one is common, and hence the pair made by the first and the last element must be there. 1, 3 must be there. Then this relation is a transitive relation. We can write more transitive relations like this. And by this is a transitive relation by first definition, but we have transitive relation another definition. By second definition, I'll write some transitive relation. If we have only 1, 2, yes, this is a transitive relation by second definition. 1, 2 is there, with 2 no other pair is there, and hence it is a transitive relation. I can write more transitive relations. Say 1, 2 is there, then 2, 3 also no. 1, 2 is there, then 1, 3 also is there. Then also it is a transitive relation. 1, 2 with 2 no other pair, 1, 3 with 3 also no other pair, and hence this both relations are transitive by second definition. So these are some examples about different types of relations. Now in the next video we will solve exercise 1.1 from textbook, and it will be available in the playlist.